Hello everyone, in this video we're going to be solving a question on solubility. We're going to be solving the solubility in the water in moles over liters and grams over liters, and then we're trying to figure out the solubility in the presence of a common ion and then in case of the formation of complex ion. So let's start out with finding the solubility just in water. So we got this solution of AgCl and the KSP is given. So if I want to go ahead and write down the general equation, it's going to be AgCl solid, and it's going to be in equilibrium with Ag plus aqueous and Cl minus aqueous. So if I want to go ahead and write down how much of the Ag plus and the Cl minus you're going to be making at the end of the day, initially you don't have any of those. And if you want to go ahead and make a nice table, that's fine, but you don't have anything, and you're not going to be really writing this silver chloride solid in your KSP expression. So just assume you have 0 here in the initial, and then figure out what's going to be the change. And a lot of time you don't really write a typicalized table in case of solubilities, but it's okay to write it. So if I lose some amount of AgCl, then I'm going to be making the same amount of this Ag plus and the Cl minus. So I'm going to be writing plus X here, and then at the end of the day, I'm going to have X here, and I'm going to have X here. So then the question is, what's going to be these X values, which is also going to be your molar solubility. So before we do that, let's go ahead and write down the KSP expression here, which is going to be the concentration of Ag plus times the concentration of Cl minus. So the KSP is given to be 1.77 times 10 to the minus 10, and your Ag plus and Cl minus is going to be the x times x, which is going to be x squared. So to figure out x, I will take square root on both sides, and then your x here is going to be 1.33 times 10 to the minus 5 molar. So right now you figured out the molar solubility in moles over liters, or another way of saying in molarity. So that's what the molar solubility is. But a lot of times you might be given or you might be asked to figure out what's going to be the molar solubility either in grams over liters or maybe in just moles over liters. So if you ask to figure out the molar solubility in grams over liters, don't forget to convert that moles into the grams. So right now, I know the molar solubility in moles over liters, which is going to be 1.33 times 10 to the minus 5 moles divided by liters. And then I can go ahead and convert this moles to grams now, and we're going to be talking about the molar solubility of AgCl. So I can go ahead and write down 1 mole of AgCl here, and on the top, grams of AgCl. So you got to figure out what's going to be the molar mass of AgCl here. Atomic mass of silver is 107.8, and then chlorine is going to be 35.45. So that's going to be roughly 143.25. Okay, so doing so, your moles of AgCl will cancel out, and that's going to leave you with grams of AgCl per liters, and that's what we were trying to figure out, what's going to be the molar solubility in that case. So when I multiply 143.25 by 1.33 times 10 to the power negative 5, it comes out to be 0.00191 grams per liter. So that's going to be your solubility in grams over liters. But like I said, most common ways of asking the solubility is the molar solubility in moles over liters, but that doesn't necessarily mean you will never see a question in grams over liters. So sometimes you may be given the solubility in grams over liters, and then you would have to convert it to moles over liters. So you're going to be going opposite in that case. You're starting with grams, and then you're going to the moles Still going to be using the molar mass, however, for your conversion factor there. Okay, so now what happens when you have a 0.02 molar NaCl present? So remember, your NaCl is a strong electrolyte, and this NaCl is actually going to get broken into ions. So NaCl, when it gets broken, you're going to be making Na plus, and you're going to be making Cl minus. So I can easily say the concentration of Na plus is going to be 0.02 molar, and the concentration of Cl minus is also going to be 0.02 molar. So we can clearly see here that in the original equation, we have the Cl here, and now we got the Cl here, Cl minus there. So that's going to be your common ion. So if I want to go ahead and just, copy this down here. So now try to remake this ice table. So when I remake the ice table, I already have some Cl minus present in the solution. So I don't have any Ag plus, but the Cl minus already present in this NaCl solution that you're trying to dissolve AgCl into. So it's going to be 0.02 molar present already. So then I can say, okay, I'm going to be making X amount of this Ag plus and plus X amount of the Cl minus. So at equilibrium, I'll have X here and 0.02 plus X here. And then the rest of the stuff still going to be very similar. So you're going to go and write down the KSP here, which is going to be the concentration of Ag plus, which is X, and then the concentration of Cl minus, which is going to be 0.02 plus X, and obviously that all that's going to be equal to 1.77 times 10 to the minus 10, because remember that's your KSP value. Now you can easily assume here that your 0.02 plus X is going to be approximately equal to 0.02, and that's because this concentration, 0.02, is actually a lot bigger than this 1.7 times 10 to the minus 10. And in that case, it's easy to ignore that plus X there. So when you do so, this equation is going to become X times 0.02, and that's going to be equal to 1.77 times 10 to the minus 10. So this X at the end of the day is going to be 1.77 times 10 to the minus 10 divided by 0.02. So when I do this math, let's see what that's going to be coming out to be. So divide that by 0.02, that comes out to be 8.85 times 10 to the minus 9 molar. Now, what happens when you have a common ion? Does the solubility increase or does it decrease? Well, common ion decreases the solubility, and if I go back and check what was the solubility earlier, the earlier or solubility in the water was 1.3 times 10 to the minus 5. But now, what happens to the solubility when you have a common ion? Well, it goes to 8.85 times 10 to the minus 9. So clearly it has been decreased dramatically from what we have originally just in water. So that's why we said the solubility is always going to decrease when you have a common ion. Well, what if you have a complex ion? So like in this case, we got a complex ion here. How's that going to affect the solubility? So let's look at this 0.2 molar NH3, and it makes a complex ion. So let me go ahead and write down the equation for the complex ion first. So it's going to be Ag. Now, how do you really know what's going to be the equation? Well, you can write the equation based on what your complex ion is going to be. So if I go ahead and write that down here, it's going to be Ag NH3 2 plus. So that's going to be your complex ion. So to make that, I would be needing one Ag plus, obviously, and then I'm going to be needing two ammonia. So I'll go ahead and add up two ammonias there. So all of those are going to be aqueous, nothing is solid in there. And this Kf is given. So for the complex ions, you're going to be given the Kf, which is the equilibrium constant for the complex ion formation. And then, 10 to the 7. And then, in addition to that, I want to go back and look up my the original equation. So I'll just copy that down here. So that needs to be looked at as well. So remember, this equation, as soon as it makes this AG plus, this AG plus gets used in the next step to make this complex. So what's going to happen? If you're using up some of your products, you must remake those products from the reactants, and as a result, your solubility is going to increase. So we're going to try to figure out how much that's going to increase. So we know the KSP here is going to be 1.77 times 10 to the minus 10. So we know those two equations so far. So what we're going to do now, we're going to add those up. So when we add those up, we cancel anything that's common on both sides. So obviously this AG1 plus is the common on both sides, so that cancels out. And then write down what's left behind. So we're going to have this AgCl solid plus 2 NH3 aqueous, and then we're going to have the Ag NH3 2 plus aqueous, and then Cl minus aqueous. So what's going to be your, I'm just going to move this to the left side a little bit. What's going to be your K, or equilibrium constant here now? What happens to the equilibrium constants of those two reactions when you add up the reactions? Well, they get multiplied. You're going to have the KSP times the KF. So whatever you get here, so that's going to be your 1.77 times 10 to the power negative 10, and then times a 1.7 times 10 to the power 7 there. So this is going to be actually 0.0030 at the end of the day. So then let's figure out what we know so far. We are told, if I go ahead and remake the ICE table here, so we don't have to worry about the AgCl because that's a solid, so I'm just going to cross that out. However, we are told we have 0.2 molar of this NH3, and since we got 0.2 molars of that, assume we don't have any of those in the beginning. So if I lose 2x amount here, so that's what I'm going to be losing here, because remember this 2, and it's usually easier to kind of write 2 in front of it in that case. So I should be making x amount here and should be making x amount here. So at the end of the day, I should have 0.2 minus 2x here, x here, and x here. So when I'm writing this new equilibrium constant expression, the K, that's going to be the concentration of your Ag NH3 2 plus times the concentration of Cl minus, and that's going to be divided by the concentration of your NH3 to power 2, because remember that's going to be, that has a coefficient of 2, so that becomes your power, and you don't include your AgCl in this expression because it's a solid. So now it's all about going ahead and putting those values in. So it's going to be 0.003, and that's going to be equal to x here and x here on the top. So in the bottom, you're going to have 0.2 minus 2x to the power 2. Okay, so then from here, we can do x squared, divide that by 0.2 minus 2x squared. And to solve this square, I can take square roots on both sides. So let me just go and copy these down here. So let me square those. Square root, take the square root on both sides. So then your right side is going to look like x divided by 0.2 minus 2x, and your left side is going to be 0.055. And then it's all about figuring out what x is going to be now. So do your math here however you want. So you can do the cross multiplication where it's going to be 0.055 and then times 0.2 minus 2x, and that's going to be equal to x. So that's going to be, that's times 0.2. This is going to be 0.011 minus 0.109x, and that's going to be equal to x. So take your x terms on one side, so that's going to be 0.011 equals to 1.109x, and then your x is going to be 0.011, divide that by 1.109, so it's going to be 0.00992 molar. So that's going to be your X value. And if you go back and figure out what the X value is, your X is going to be representing the Cl minus. And that was one of the products that we were making when you had the AgCl broken into the ions. So that would have been your molar solubility. And you can clearly see how this molar solubility has been dramatically increased because now it's almost in terms of scientific notation, is going to be 9.92 times 10 to the minus 3 molar. And in the absence of that, or just in water, it was 1.33 times 10 to the minus 5. So your molar solubility increases in the presence of complex ion formation, and it will decrease in common ion. Okay, so this is how you're going to be doing these complex problems where you have, everything basically in water, in aqueous solution, or in common ion and in complex ion formation. If you have any questions on any of those, feel free to leave any comments in the section below.